Now let's look at a different example where loop 4 is not so straightforward to use. And why is it so? Well, we want to add up a bunch of terms, but we want to keep adding as long as we haven't reached 1 million, and we stop once 1 million has been exceeded. So also the formula, the way it looks, already suggests that we don't actually know the number of steps which has to be taken in order to complete it. So this is a natural situation where we would use loop while rather than for. And the task is to figure out how many steps exactly. So that's the actual task, how many steps it takes, how many terms of this sum have to be used in order to exceed 1 million. Okay, so let's do it. We had, let's clear the space. We know that we are going to count number of steps, so I like to use variable n for it, and before any steps have been done, of course, that number is 0. Now, what are we summing? It's a bunch of terms where pairs of numbers are multiplied, and luckily these numbers are related in the pair, so it's always a number multiplied by itself increased by 1. So this is good news for us because we really can use a loop. Normally you cannot use a loop if there is no pattern in for instance, how the sum is behaving. If it's completely irregular, you would have to do it manually. But in this case, we know the pattern. So we know that our base number starts from 1. It gets multiplied with itself increased by 1, and then the next one is by 1 bigger. So what we can do is start with x equal 1, and then we construct our loop, in which first I will actually do the content of the loop, and then we will write the condition. Of course, we also need our sum, and that one starts from 0 initially. So when 0 steps have been done, the sum equals 0, and our starting point for the sum is x equal 1. So then what we have to do is increase that sum by that term, and the term is the number multiplied by itself plus 1. Now, since I have done this, so I've increased my sum by 1 more term, I have to count that I have used that term. So that's where I increase my counter n and leave. And now all that is left in here is actually write when should this loop stop, or rather how long it should be running. So remember that condition in while, that expression means as long as it is true, keep running. Our goal is to exceed, with our sum, exceed 1 million. So it means that as long as I have not reached 1 million yet, I want this loop to keep running, and that's why that condition here should be written like this. Let's just write 10 power 6. So while this is true, as long as this is true, so as long as I don't have 1 million yet, or it even says it should be exceeded, so less equal. So in case we are exactly on 1 million, we would have to take 1 more step. So as long as we haven't exceeded 1 million, add 1 more term to our sum and check again. So let's run this and see what was that number of steps. So it seems like it's 500,001 exactly. It looks suspiciously big if you think of it, and yes, I just realized the mistake, because now what is happening, our x here is always using this initial value x1, so I have forgotten that of course in our loop we increase the sum, we increase the count, but we also modify x for the next term. So here, once I've done my sum, I should have said that x gets increased by 1 as well. So now when we run this, we have, yes, much fewer steps, and this looks much more reliable. So remember, because we were adding terms which are not all of them 1 times 2, 1 times 2. They're 1 times 2, 2 times 3, 3 times 4, and so on. So now it's done correct. And just as a recap, to display our results, we can then use fprintf, and I will say in here we need n steps. I think I was for integer, or I terms in the sum in order to exceed 1 million. We could also actually have this 1 million defined as some kind of threshold. And so we also use that, so that in case we want to change the parameters here, we can do it as well. So I want to put n and threshold values in here. And there is our answer. So we need 144 terms in the sum in order to exceed 1 million. And then how about we ask one more thing? For instance, how many terms or how many numbers, consecutive natural numbers, we have to multiply to exceed 1 million. So now we would like to do something like this. So there will be a small difference how this is done, because now we're actually not summing, we're not adding things up, we are multiplying things up. So I will use my base construct of the loop once again. Threshold is the same, but now, as I said, we are multiplying, we are not adding. So it is called product. We are having a product of numbers. So in this case, I will call it, let's say, p. And when you start multiplying things, first you start with 1, because it's only when you multiply something by 1, you kind of get the same thing at the start. So product, when you have to multiply many things in a loop, you have to start from 1. And then what is happening here is that then I take that product, and it will be that product that I will have to multiply with my next x. So now if we look at it again, that we want x to be starting from 1 and going as long as it takes, so I should have also defined x here as 1 once again, and take that count once again as 0. So now I start my multiplication from 1, and then take the first term, multiply my previous product, and assign it as a new value for that product, and then I increase x for my next step, and I also count the number of steps. And then here, of course, now I'm checking the product and not the sum. So as long as my product, so the multiplication, is not yet exceeding 1 million, I keep going in the loop. So let's take this one to display results. We need items in the multiplication in order to exceed 1 million. So this remains, and n can now remain here because we are not using that n anymore. It has been overwritten by this new n. Okay, so we run. Oh yes, I forgot the new line, so let's put a new line here, and let's also put one at the end of this and run it again. So we need 144 terms in the sum in order to exceed 1 million, and we need just 10 terms in the multiplication to do the same.